everyone. First of all, thanks very much for the invitation to speak here today. It was really great to see some of the startups this morning and some fantastic things going on around the exhibition. Very, very inspirational stuff. Today I'm going to talk to you a bit about what we're doing in the Quantum Technology Hub in Sensing and Timing in the UK. So I don't have time to show you everything. I've decided to focus a bit on some of the methodology and some of the trials that we've been doing. But then if you have more questions, please feel free to drop me a message or contact me for a discussion at the time. And I'll be around for the afternoon. So first of all, just a little bit about the quantum program in the UK. So if we roll back the clock to 2014, we saw an investment from the UK government of about £1 billion into quantum technology. And this was to take the existing quantum science in the UK and turn that into technology devices. They divided the program into 4 main areas, so sensing and timing, and we have a research hub leading that work at Birmingham. Communications, so quantum communications, led by York. Quantum imaging, led by the University of Glasgow. And quantum computing and simulation, led by Oxford. So this is just part of the program, but these hubs have then existed to coordinate the academic communities in those areas and act as a focal point for collaboration with industry. In addition to that, we also have bodies such as the National Physical Laboratory, where they have new labs there, and the National Quantum Computing Centre to coordinate the overall program. What's quite exciting is that recently the government has announced an uplift to the program, wanting to invest another £2.5 billion over the next 10 years. So now I'll tell you a bit about our hub. You can see some of the partners here, and I'll tell you a bit about what they're doing as we go on. But our hub is really a group of around 100 researchers, if you include all of our teams, working very closely with industry. So we have roughly 230 projects separate to the hub but linked, where we're working closely to understand what do end users want to see from quantum sensors, what do we need from the supply chain, how can we enable the supply chain to deliver for those end users. And this has led to a large program where we're helping to coordinate projects across all the different areas we're working in. And it also has really led to now quite a lot of invention, new ideas, new processes, new ways of solving problems in the quantum technology area. And this is now starting to see some products come up and spin-outs out of the academic areas. So quite a focus of the hubs, although we're an academic community, is really to act as a focal point for bringing together the industry community. So these are some of our partners. And one of the key features of the hub is really to connect those people in the supply chain to the end user requirement and help understand who owns the problem, who benefits from the problem being solved, and how can we evidence a need for that market. So quite often what we see is the people that will benefit the most from the sensors being there are not going to be the ones who will want to pay for that market to be delivered. And if we want to justify the kind of investment that we'll need to see to take some of the devices that I'm going to show you from the size they are now into something the size of a Coke can, we will need a lot of investment in quantum sensing. So it's important to evidence that, and that's why there's a strong push for connecting the value chain, linking companies like BAE Systems or RSK to people in the supply chain where they're really understanding what they need to build. So in the hub, the way we do this is by creating demonstrators where we can show industry what our quantum technology systems can do in applications. I won't read them all out now, but I'll show you some examples of what we're doing in a moment. The hub is focused in particular on atomic sensing. We help people from the other sensing areas as well, but most of our research is based on either atoms or MEMS. And as an example, what you can see here, this is a cloud of cold rubidium atoms inside one of our traps. It's about 100 million atoms trapped with a laser and magnetic fields. And what we would do, for example, is with each of those atoms in the cloud, put them into something called a quantum superposition, where if I shine a pulse of light on some atom, when the light finishes the pulse, the atom has a probability of being in one of 2 quantum states, and I can tune the probability that it's in one or the other by the intensity, the frequency, or the amount of time that I apply the light pulse for. And if I do that just right, I can, after my light pulse, have a 50% chance that this atom has absorbed some light or not absorbed some light. And when it absorbs the light, it gets a little kick of momentum. And what that does is it means after some time, the atom will exist in these two states, which will physically separate, and we end up with the atom in two positions, and it doesn't know which one it's in until we make a measurement. And so, for example, if I were some mass and I stood down here, I would pull the bottom one slightly more than the top one, and that difference is something that we can actually measure. So that method allows us to, for example, measure mass, or if we change the direction in which we apply the laser beams, we can measure acceleration or rotation. Using similar techniques, we can also measure time and magnetic fields. Now, I'm just going to go through and give you some examples of some of the demonstrators that we've been working on. So the first I'll talk to you about is gravity gradiometry, where working with people in the civil engineering sector, we recognize that actually the inspection technologies that are used at the moment are really limited in how quickly they can look into the ground. So you have techniques such as ground penetrating radar, where it can see into the ground quite quickly, but it's often quite limited by changes in the ground condition. So whether it's damp, whether you're on particularly solid ground or not, can change exactly what you see. And one of the favorite technologies for seeing into the ground is gravity sensing, except it's too expensive because it takes a long time. And the reason it takes a long time is because the ground is always slightly vibrating, and we can't tell the difference, due to Einstein's equivalence principle, between vibration and gravity. So what we did is we used a technique that suppresses vibration very, very strongly. So rather than measuring on one cloud, we actually perform the measurement on two clouds at the same time with one laser beam. And this one laser beam means all of the noise on the bottom measurement is exactly the same as the noise on the top one. So if we take the difference of the two, we still have some information about the gravity gradient, but we lose all of that noise. And what that could mean is, in principle, being able to scan rapidly and image things under the ground at a speed that's only limited by how sensitive our device is. And this could be really game-changing, because if I make any gravimeter more sensitive, I'm just measuring the vibration better, whereas this manages to get past that technique, or past that limitation. So that's what we did. We built a gravity gradiometer. Sorry, it doesn't show very well in the pictures here, but this is the system in a cave where we put it there to test its resilience to the environment. This is the system here. So we have a tall tube where this measurement technique is happening both at this height and this height. You can see what the insides look like here. And this system was able to perform these gravity measurements in the field, in outdoor conditions for months at a time, without any need for realignment or optimization. So we start to see things getting very, very robust. And what we showed in 2021 is if we take that sensor and we move it over a road, this is a scale CAD drawing here, when it gets to the middle of the road, we see a dip in the gravity gradient, and that corresponds to a tunnel that's buried beneath the ground. And now to give you a comparison with classical technology, here we saw that in the measurements we performed, it was roughly 4 times better than classical technology, but in principle, with this sensor, if we could get over the fact that it's quite large and cumbersome, it could detect the tunnel within about 15 minutes compared to a day of measurements. So there's a lot of potential there, but engineering is needed. And this removal of the vibration means, actually, in principle, we can much more rapidly scan areas at high resolution and find things much quicker under the ground. So it could open new ways of monitoring water, new ways of looking at underground infrastructure, new ways of navigating. And this is something that we're now starting to do trials on. So here you can see the system being operated on a ship. Sorry, it's not very obvious it's on a ship in this picture, but you can see here's the sea, and here's some windmills that are being used to generate power. And here we're looking at, can we use it as a navigation system where if I was to travel through this map and I measured the gravity gradient as I went, it could allow me to position without the need for something like GPS. Another area we're working on is quantum clocks. So here what you see, this is some work by the University of Birmingham where they have integrated a quantum clock into a small box. And this, they believe, is the smallest physics package for an atomic clock now, where they can put that into a little box that's about 120 litres. And in principle, that could allow transportation of time, comparisons of time in different locations that could open new applications in relative geodesy. And this is another clock from the University of Strathclyde where we're starting to see clocks being packaged up in a way that they could be taken out of the lab into practical environments. One of the applications we're really interested in there, and we've started doing some trials on that, is using these clocks to provide a very low phase noise for a radar system. So a radar works by sending out a pulse and looking at the time it takes to come back. And if we can discipline the radar signal with a very precise phase, very precise time, then it means we can make much more accurate measurements of where things are. And in principle, this could be used to reduce the clutter in environments and could be used to enable radar systems to spot drones in cities, maybe as a tool for predicting where drones are going to go by looking at what their motors are doing. Then we've done a lot of work in the hub on sensing of the brain. So what you can see here, down here, this is a little helmet where it's been covered with a range of optically pumped magnetometers. Those are used to measure the magnetic field of the brain. And by putting that inside a magnetically shielded room here, we can get to a low enough ambient field that actually we can make measurements of what the brain is doing, look at how patients are reacting to certain stimuli. So you can imagine letting someone read a book and seeing how their brain is reacting to that, or allowing them to move around and seeing how they react to that. The challenge is that most brain sensing technologies, such as a conventional MEG system, you have to be in a hospital in a very well cooled and contained environment, so they need cryogenics. With these technologies, the team at Nottingham hope they can take these things into maybe every GP could have a brain helmet inside, so that rather than having to go to the hospital every so often, you could routinely have your brain checked. Maybe everyone could have a brain scan at 40 to see if they have any aging health issues, or look at how people are responding to stimuli in a more natural environment. And so this led to a startup from the University of Nottingham Circa, where they've started selling these rooms and sensors to allow hospitals to start diagnosing people with epilepsy. We've also got work going on in the hub involved in MEMS sensing. So what you can see here, this is a little light source, and down here they have something about the size of a postage stamp, which is a very little mass on spring device where they use nanofabricated silicon, and by looking at the deformation of that spring, they can make measurements of gravity, and they hope to be able to make very cheap compact gravimeters with this technology. Here you can see one of the postdocs in the hub who's using one of these little sensors on Mount Etna, and there they're looking at, can they use these things to look at magma flows or underground water movements, this kind of thing, hoping to be able to make cheap arrays of gravimeters for environmental science type applications. And we also have work on inertial navigation. So quite recently, this was probably in May, I think this year, the Imperial College London team have installed their quantum accelerometer onto the back of a ship and looked at measuring acceleration while the ship is moving up and down the river and out at sea. And there the point is that actually when we start measuring with atoms, every individual atom is it's identical to any other atom, which means when we make a measurement, there's a very good opportunity for getting very low drift measurements, meaning that the sensor won't change unless the measurement that it's making will change. So it gives us a way of potentially reducing the drift of inertial navigation systems, allowing accuracies that are beyond what we can do now, even in GPS-denied environments. And that's where they're trying to take that activity. And I think finally, we're also doing work on building gravimeters that can operate at much higher bandwidth than current gravimeters. So here, this is one of the systems at Birmingham that can run at about 100 hertz. So here, this fringe of gravity measurements made in about a second with about 30 measurements in that time. Unfortunately, I can't show you the video because this is a PDF now, but here, this is a rapidly generating and collapsing cloud. And they're trying to use that both for navigation applications, but also as a tool for making better predictions of the distance between the Earth and satellites, so we can have a better satellite laser ranging system. And this could be really important for a host of different things, such as any Earth observation. Having a better idea of where the satellite is will reduce your errors in, let's say, laser scanning or other terrestrial applications. And so that's what we're doing. I think that the point of what I'm trying to show you is that our sensors are really starting to not be things that are contained in labs anymore. And so I think this is really quite an exciting time for quantum sensing, where even atom interferometry-based systems, which are quite complicated, we can see them working in some quite challenging dynamic environments and still being able to measure. And this, I think, is really promising in starting to see quantum sensing really reach quite deeply into applications. Here's just some of the different areas we see being very interesting. So for sensing into the ground, actually in the UK alone, it costs society about £5 billion a year because holes are dug in the wrong place and people don't know where their underground infrastructure is. This leads to road congestion that we could in principle stop by having a better tool for reading what's there. By better diagnosis and monitoring of people with dementia or ADHD and epilepsy, we could in principle reduce, help with their symptoms, or maybe even solve some problems, provide new avenues for research. There's a growing number of drones flying in the skies, and having better ways of spotting them is an important thing. In the UK, we've had drone incidents where a single drone has cost £50 million by flying around near airports, and no one could tell where the drone was. And then it turns out there's just someone playing with the drone in their back room. So being able to spot and know where those things are going to go in the future is very important. And finally, position, navigation, and timing is especially being able to do that in remote or challenging environments is a growing problem where relying on GPS becomes, a less and less sensible thing to do. And this is one of the areas we're really pushed to look into in the UK. And so, as in part due to these applications, but of course there are a lot more. Quite recently, the World Economic Forum singled out quantum sensing as one of the top 10 technologies to be looking at. So I hope I've convinced you that it's worth a bit of attention. So, thank you very much for listening. If you have any questions, please find me afterwards.